Okay, so yesterday we started to graph basic square root equations. Today's pretty much going to be the same. We're just really going to introduce coefficients. So like I said yesterday, yesterday's and today's is basically normally one lesson. I kind of cram it all together. I said things remotely are a little bit different, so we're going to try to stretch things out a little bit here. So we're going to do this over the course of 2 days instead of one. So that being said, for this one, right, we're going to put this in our calculators, and we're going to try to find the values that are not going to be imaginary numbers, right? So the ones that don't say error or no, non-real number. We also really don't want radicals or decimals unless we have to. So the smallest value we can use is going to be 1. And then we're going to have 2, and then we're going to have 5, and then we're going to have 10. And if we add space, I guess we can go out to 17. So when I substitute 1, I get the square root of 1 minus 0, which is square root of 0 is 0 plus 2. 2 minus 1 is 1, square root of 1 is 1 plus 2 is 3. And again, guys, you're pulling these right from your calculator. 5 minus 1 is 4, radical 4 is 2, plus 2 is 4. 10 minus 1 is 9, radical 9 is 3, plus 2 is 5. And 17 minus 1 is 16, square root is 4, plus 2 is 6. So I'm going to graph, and I start with 1, 2. I've got 2, 3. I've got 3, 4, 5, 4. And I'm all the way out at 10, 5. So again, guys, what we're going to notice, there will be an arrow on this side, okay, because, we do have to eventually try to get to 17, 6, or at least show that the graph does go out there. But no arrow on this side, right? There are no negative, I can't use 0 as x or negative 1 or negative 2 or anything like that. So my domain, my x values are x is greater than or equal to 1. My y values would be y is greater than or equal to 2. Okay, so again, only an arrow on one side because it does not go infinitely to the other side. It only goes infinitely to the right. And again, today's lesson is really kind of just an extension on what we did yesterday. So since this is just radical x, I want x to be my perfect squares. So I've got 0, 1, 4, 9, and 16. So the square root of 0 is 0 times 2 is still 0. The square root of 1 is 1 times 2 is 2. Square root of 4 is 2 times 2 is 4. Square root of 9 is 3 times 2 is 6. Square root of 16 is 4 times 2 is 8. And if we had more space here, we would make this go out to 25, 10. So one thing we could do is we could set up the x-axis in terms of using intervals of 2 and the y-axis in intervals of 1. I'm not going to do that. I'm going to keep it as is, but that would give you maybe a nicer looking graph. So let's just graph these. And again, these values we're going to pull probably right from our calculator. So we have 0, 0. Right, I've got 1, 2. I'm going to go out to 4, 4. And 9, 6. Right, so what would we say happens to our graph? Right, so this is y equals 2 radical x. Well, I would say that graph got wider. Okay, so if we look at my first one versus this one, it definitely looks to me like if I was to fill out the other half of this, which would go down to negative 6 down here, and that's not the actual graph, but it would certainly be a lot wider than if I filled out the other part of this, which would look more like that. So what do we notice, right? Changing the coefficient outside the radical to 2 is going to make our graph wider, which is strange because it's the opposite of when we have a quadratic equation. When we have a quadratic equation, if I graph y equals 5x squared, that's going to be really what we call narrow, versus x squared, which is going to be a little less narrow. Okay, so it's going to be a little different. The reason it's a little bit different is because in order for us to solve for y here, we would have to square both sides, which would give us 4, and then times x. So 2 squared is 4. Anyway, that's why it ends up being wider. Now let's see what happens when we've got the radical 2x, or the 2x is inside the radical. So we want to be kind of careful with this one. I mean, again, I'm not using the calculator, but using the calculator, it's not going to matter. You're just going to have to pick and choose the values that you're going to want. So I know that I've got 0, 0. Now I can't use x as 1. That's going to, I mean, I could. It's going to give me radical 2. So the next value I'm going to use is x is 2. So when x is 2, 2x is 4. And the square root of 4 is 2. Now it's going to get a little tricky, right? So if I really want to be technical about it, and this one you're not going to see in your table unless you change your table setup, I really want what's in my radical to be a perfect square. So this first one features the perfect, actually, you know what? Let me go back even to further illustrate this. So if I want what's in my radical to be a 0, I make x 0. What I did for the next one was I wanted to make it 4. So the square root of 4 is 2. But what about the square root of 1? Well, in order for me to get 1, I would have to use half. So that's not to say I'm going to graph this necessarily, but I do want to show you that if I really want all of my perfect square values, that's what it would be. And again, you're not going to get that without going to table setup. What if I want the next perfect square, which is the square root of 9? Well, in order to get the square root of 9, I would have to make this 4.5. So the square root of 9, right, because this is now 2 times 4.5, which is 9. And that's going to be 3. Now, what's my next perfect square? 16. How am I going to get that? I make x 8. So if x is 8, 2x is 16. The square root of 16 is 4. And my next one is 25. So if 2x is 25, x would have to be 12.5. And then I get 2 times 12.5 is 25. Square root of 25 is going to be 5. And if I really want to go a little bit crazy here, I use 18, and 2 times 18 is 36, square root of 6, just so that all my y values are integers. Now, do you need to plot all of these values? Of course not. Right? Again, you're not going to see these decimal or fractional values unless you go to table setup and change it to halves. Is that necessary? Not really. You're just going to be your graph's going to look like it's missing some points. So we're going to start at the origin. Right, my next point here is going to be, I'm not going to do the fractional points, but I'm going to show you how they are there anyway. That was kind of my purpose in doing this. Right, so those are the points that I actually can fit here. So I'm going to try my best here to make this nice and smooth. And again, the arrow will be here because I have to get to 12.5, 5. I have to get all the way out here to 18.6. So maybe I should make the arrow look kind of like it's slanted upward a little bit. I like that a little bit better. Now, what about the points I didn't plot? Well, they're there. Where's a half comma 1? It's there. I didn't plot it, but it's there. Right? Where's 4.5 comma 3? Well, it's exactly right there. Right? I didn't need to plot it. By connecting the points around it, I actually go through that point. So it's not necessary to plot those fractional values, but we do want to make the connection that even though we didn't physically put a point there, that they are in fact there. And again, I tend to get lazy sometimes or just kind of careless or forgetful. We want to make sure that we're going to be labeling our equation as well, y equals radical 2x. All right, and then as far as the connection, right, the width here is going to be pretty similar to this first one. It's actually going to be somewhere in between as far as the width. And let's look at what happens here. So now I'm back to wanting perfect squares, but a lot of these answers are going to give me decimals. So I want radical x and then divide it by 2. So 0 is always going to be a nice easy one here. I could use 1, right? But what's it going to give me? Well, the square root of 1 is 1, divided by 2 is half. So again, I'm going to avoid plotting those unless I have to, and sometimes we have to, and we talked about this before. And my x values, I only want perfect squares, so I'll use 4. So the square root of 4 is 2 divided by 2 is 1. 9 is not going to give me such a pretty one. I mean, it's just going to be a decimal, right? So square root of 9 is 3 divided by 2 is 1.5. We're going to jump now out to 16 here. Square root of 16 is going to be 4 divided by 2 is 2. And I'm sure we've noticed this, that there's always going to be that pattern in the y, the y values. Normally, it's a pattern of 1 if I use perfect squares. In this case, it's a pattern of half because of the denominator being divided by 2, which is the same as saying half radical 2, half radical x, right, if we wanted to rewrite it like that. So my next value, if I use 25, is going to give me 5 halves, or 2.5. And again, if we want to get a little bit larger with our values, we're going to get square root of 36, which is 6 divided 2 is 3. So let's see what this happens if we don't change our scale. And then maybe let's go back and say, maybe I had to change my scale. So I've got 0, 0 here. I'm going to go to do 4, 1. 16, 2 is going to be a little bit tough. That's not really going to fit. So I can do 9, 3 halves. So that's not horrible, right? So that's what it's going to look like if I keep my scale the same. which I tend to want to do so I can compare it to the rest of them, right? How did this compare to something like this? Well, this is radical x with the coefficient of 2. So we said that's going to make it wider. So if it was 3 or 4 or 5, it would make it much wider. Now this is different because it's inside. It doesn't have the same connection. But here, what's the coefficient? If we want to think about this as something times radical x, the coefficient is half. So if increasing, making it 2, 3, 4, 5 is going to make it wider, then what we talked about is a fraction is going to make it narrower. And again, this is opposite what happens with the quadratic, right? In other words, if I do half x squared, the connection was it made, with the quadratic, it made it wider. These are square root functions, so they actually behave in the opposite direction because it's y that's being squared instead of x. So in this case, like we said, it's going to actually be narrower. But the connection here is the same, that there's a point here with no arrow and an arrow on the other side. So for the most part, what we're doing here, guys, is we're leaning on the calculator. Now you're going to put the equation in your calculator. You're going to plot the integral values, as in the ones that are not, imaginary numbers, obviously, and the ones that are not decimals, unless you have terminating decimals like this, and that's going to be it, and you're going to label it. So your homework should actually be pretty simple, just like it was pretty simple last night. 2 different graphs, and again, if you don't have graph paper, everyone should have their graph notebook. You can print out a piece. 2 different graphs. So on the first graph, you're going to have the first equation, 4 radical x plus 1. So your x value should be perfect squares. And the second one is y equals radical 4x and then plus 1 outside. So your x values should be the ones that give you a perfect square inside. Things like 0, things like 1, things like 1/2, things like 4. All right, so that should hopefully be nice and easy. But as always, guys, any questions, comments, concerns, send me a message in the comment section of the homework assignment.